Good morning, dear students. Last class we discussed about requisites of laser system and also a condition for laser actions. So, continuation of these two concepts. Today we will discuss Einstein's coefficient of thermal equilibrium. So, the thermal equilibrium means we are already studied in PUC and also SSLC. Thermal equilibrium means what amount of the energy we are going to supply, same amount of energy will be get back. So that one is we call as thermal equilibrium. So for this one, here we need some learning objects and also session outcomes. Learning objects is here we are going to get the information about the what amount of the intensity of the light radiations of a laser light radiation we can produce knowing the thermal equilibrium through a Einstein's coefficients. That is the applications what we are got it from the Einstein. Second one is the session outcome is through a Einstein's coefficient we learnt whatever the intensity of the laser light radiation we can produce if we know the Einstein's coefficient. And also we are going to analyze the concept of the thermal equilibrium. So here we know in a ruby laser or in a helium neon laser or in a semiconducting laser, so we are going to use different intensity of a laser light radiations. So these different intensity of laser light radiations is for different kinds of applications. Just we can imagine it. In industries, we are utilizing higher intensity of light radiations to cut the iron pieces. But here we come to the medical field. Just we are going to find out the foreign items in a human body. If you come to the class hours, we are going to utilize a small microwave region radiations to showing the a point through a laser using a PPTs in a PPTs. So it means here we require different intensities. It shows what amount of the intensity here we are going to apply, same amount of intensity will be come back. That is here we are going to understand through Einstein's coefficient. Einstein explained the thermal equilibrium. That means rate of absorption is equal to rate of emissions. Here we know rate of absorption means inducer absorptions. So it explains the meaning of the concept, that is the rate of induced absorption means how many number of electrons take part of the inducer absorption and each electrons what they have it energy densities. This is a prime part for the production of laser light. How many electrons are interact for the production of laser light and each electrons how much energy density they have it. That is we call as rate of absorptions. Next here we come to the stimulated emissions. Stimulated emission means at the time of upper energy level. So it takes the stimulated emission due to the interacting of the photons. So at the time it takes the downward transitions. At the time of downward transitions, how many number of electrons takes from higher energy level to the ground state, and all these photons or electrons having a how much energy density. That is very important for the production of a laser light. These two are very important. That is a rate of inducer absorption and also a rate of stimulated emissions. Next part is rate of spontaneous emissions. Usually the absorption is equal to emission. In this concept we have to make it a rate of spontaneous emission should be 0. It should not take place. If a spontaneous emission takes place, It means automatically without any external energy. If the electrons will be emitting the laser light radiation means, sorry, takes the emission means, so this is not a monochromatic light radiations. It release polychromatic radiations. It does not take a responsible part for the production of laser light. So we have to make it zero of rate of spontaneous emissions. So at the time we are not going to bother about the energy density. We are going to count only the numbers. That is the rate of spontaneous emission is equal to A21N2. Here A21 or B21 or B12, these are all the Einstein's coefficient constant values. 2 and 1, it explains the excited state and also a ground state energy levels. Okay, na? After knowing these three emission rates, so now here we come to the steady state conditions. That is a thermal equilibrium conditions. Rate of absorption is equal to rate of emissions. In the absorption rate, one kind of absorption equation is there, that is the rate of absorption. In the emission rate, two different kinds of emission rates are there here. One is a stimulated emission, another one is a spontaneous emissions. Now here, just here we can see in the equation number 4, the LHS, what here equation we have written, that is the rate of induced absorption. In the RHS side, we can get it two equations, that is a rate of spontaneous emission and also a rate of stimulated emissions. We want to calculate energy density. Our concept is to calculate the energy density rho of nu. So far we have to equate all these equations towards energy density to get these equations. Okay, na? Here we know A means Einstein's coefficient constant value. A21 means it is going to get the excitation from ground excited to the ground state. Similarly, B means it is also one more another constant value. So all are constant values. Because of this reason, we can rewrite these equations from in this order to in this orders. Okay, na? After that, so here we come to the main concept. We come to the main equations. Rate of absorption is equal to stimulated emission and spontaneous emission. Based on these reasons, we got a conclusion equation. The energy density is equal to A21 N2 by B21 of B12 N2 by B21 N1 minus 1. So whatever the equations here we got it, this relation is correct or not. We have to compare this equation already verified equation from the Planck. So Planck is explained in black body of radiation spectrum. Rate of induced absorption is directly proportional to the emission rate. Whatever amount of the energy will be gets induced absorption takes place by the black body, same intensity of the light radiation will be comes out from the same body. Knowing that relations, we have to verify the positional identities from the our Einstein's relations. If positional identity will be verified, our Einstein's relation will be also holds good for the thermal equilibrium conditions. That about the Einstein's coefficient relations. In this concept, we having some multiple choice questions also. So here the probability of a spontaneous emission increases rapidly with the energy difference between the two states. So the statement will be correct. Here we are given two statements. So it is the correct answer. That is answer is A. So next is the lifetime of the metastable state. Earlier I said. So the lifetime is always 10 to the power of minus 8 second. But the metastable state lifetime is 10 to the power of minus 3 second. So it means the answer is C. Similarly, third question is which law is used for achieving the relation between the Einstein's coefficient? It is that is here we called as Einstein's equations. So next is which of the following Planck's radiation law. In the further third question, the answer is Planck's radiation law. We are going to compare Planck's radiation law with our Einstein's energy density. Fourth question is which of the following Einstein's coefficient present spontaneous emission? So spontaneous emission means the atoms will be from excitation state to ground state, downward transition takes place. So it shows 2 and 1. B is the answer. A to 1. So it's about the Einstein's coefficient thermal equilibrium constant relations. Thank you.